Let's look at the gradient of a potential function. We're actually going to be more interested in the reverse problem, but doing this computation will shed lots of light on that. So if we start with a potential function, the square root of 9x squared y plus 5z squared, and actually compute the gradient, then we produce what we call a conservative vector field. That is a vector field f, which is the gradient of a potential function. Now, the reverse problem would be to show that f is conservative. That would mean showing that its curl is identically 0, and we will talk about that in later videos. But then an equivalent condition to that is that there is a potential function whose gradient is the vector field f. Now, the reverse problem is more difficult, but this helps to shed, again, more light on that particular problem. So now, in order to compute the gradient, we need partials. So the x partial of f here will be 1/2 9x squared y plus 5z squared times the x partial inside, which we see is 18xy. The 18 and the 2 absorb to give us 9, and then we have 9xy divided by the square root of 9x squared y plus 5z squared. And then, of course, the y partial will be 1/2 times 9x squared y plus 5z squared to the negative 1/2, and then, of course, the y partial of the argument, which is 9x squared, and so we end up with 9x squared divided by 2 times the radical 9x squared y plus 5z squared. And then, of course, the z partial will be 1/2 9x squared y plus 5z squared to the negative 1/2, and then times the partial with respect to z, which is 10z, and of course the 2 and the 10 reduce to give us 5, and we have 5z divided by the radical 9x squared y plus 5z squared. So all of these become the coordinate functions of the vector field f, and you can see here at the bottom I have just written them as a vector. So again, though this problem is very simple, it's very illuminating about the reverse problem, which we will spend some time on in the next couple of videos. And we are done.